Welcome Math All Day, folks. What we're going to be looking at today is a subject from differential equations called the modified Euler's method. So Euler's method is a method that's used in order to estimate the value of a function at a particular point given a differential equation and its initial condition. The modified Euler's method does the same thing, except it does it more accurately with only a small amount of an increase in the number of calculations. So if we look at Euler's method basically is going to do that estimating of a value of a function at a particular point given a differential equation and the initial value of the function. It's an iterative process where we're going to start new lines at each new value of y, and we're going to move along the x-axis at a prescribed length, which we call h. Because we've got a differential equation, the value of the slope at each one of those points is going to change from one to the next value of xy. So consequently, the lines are going to look slightly different, or they will look majorly different depending upon the kind of function you're looking at, depending upon where we are in x and y. The modified Euler's method works in a very similar manner. However, instead of using one slope found from our starting point, I'm going to use the average of two slopes, and this is going to give me a much better and much more accurate estimate for the value of my function. Let's take a look at the method and talk a little bit about the theory behind it. So let's say we have this example. We've got dy dx equals x squared minus y. We'll have the starting point of y of 0 equals 1. And let's say we have a step size of 0.5. What we're going to do first, just like without Euler's method, is we're going to find dy dx at 0, 1. So that's going to be 0 squared minus 1, which equals negative 1. Then we're going to find this thing called y1 star. And y1 star is kind of an intermediary step inside of the whole process. It's going to be the finding of the next value for y if we were only using this original slope, just like Euler's method. So it's like basically where we would end with Euler's method. So we've got y naught, my 1, plus the step size times the slope, basically drawing a line, and we end up at 0.5. Then what we're going to do is we're going to use 0.5, 0.5, because if we were to stop with Euler's method, this point right here would be 0.5, 0.5. We'd have the next iteration in x, and then we'd have our y value. We're going to then use 0.5, 0.5 to calculate the slope using the differential equation. So we're going to get 0.5 squared minus 0.5, and that's negative 0.25. Then, and this is the difference here, we're going to average the two of those. We're going to take negative 1 and negative 0.25. We'll average the two of them by multiplying 0.5 times their addition, or 1/2 times their addition, and that gives me negative 0.625. So essentially what we're looking at here is if we started at 0, 1, and we constructed the slope of 1, and we went over 1/2, we'd end up at 0.5, 0.5. And then if we did this again, the new slope that we get from 0.5, 0.5 would be at negative 0.25. So we have a slope here of negative 1, that's our first slope, and we have a second slope of negative 0.25. Then we're going to take an average, and that average, right, is going to be the average between the two slopes, not necessarily halfway through there. We kind of imagine it would be kind of an intermediary step. It would be not as steep as negative 1, but more steep from negative 2.25, so negative 0.625. That's the slope, and that's going to be our new slope. What we're going to be doing with that is that we're then going to go find our y1, our next step in the iteration. So we have that new slope, that average slope. Then we're just going to go find y1 by taking our y naught plus the step size times the average, and that gives me my new value of 0.6875. So our new actual x1, y1, the one that we're going to use in the iteration of the process, is going to be 0.5, 0.6875. To find x2, y2, we'll just repeat the process. Now, let's talk about symbolizing the modified Euler's method, a way of kind of like writing this down so that we can think about it in just in terms of a general term. So we suppose that we have a differential equation f of xi, yi with an initial condition x naught, y naught, and a step size h. The number of steps n is going to equal the difference between the value of x we are seeking and x naught divided by h, and we'll look at that instead of our example. Our first step is going to begin at x naught, y naught, and it's going to be yi plus 1 star, and it's going to be yi plus h times f of xi, yi. So that's our Euler's method right there. There's Euler's. Directly from Euler's method. Our second step, though, is we're going to use the average of f of xi yi and the differential equation evaluated at the next step in x and the step that we got here from our first step to calculate our yi plus 1. So our yi plus 1 is going to equal yi plus h, our step size, times, and this thing here, that's that average. We're going to continue to iterate until we found the nth iteration of y, until we finally find that nth iteration, and we're done. Let's take a look at an example. Let's suppose I have dy dx equals y minus x, and we're going to start at 1, 3. We're going to have a step size now, again, of 0.5, and we want to find y of 3. So our first step is to find the value of the differential equation at 1, 3, and that ends up being equal to 2. 3 minus 1 is 2. Then we're going to go find yi star, which is our intermediate step, and that's going to be our y plus our step size times 2, and that'll equal 4. So now we've got this intermediate point called 1.5 comma 4. We're then going to utilize 1.5 comma 4 to find the value for the differential equation, which in this case is going to be 2.5. To find y1, we're then going to take our y0 plus our step size times our average, and that ends up giving me 4.125. Now we're going to do our second step. We're now going to be at 1.5, and notice our 4.125. So we've iterated 1 up by 0.5 and gone to 4.125 for y. We'll go find the slope there, and that slope ends up being 2.625 using our differential equation y minus x. Then we'll find our y2 star using that Euler's method, and that gives me 5.4375. I go in again, I find the value of my differential equation now at the next step, or this next intermediary step, at 2, 5.4375, and then, which ends up, by the way, giving me 3.4375, and then my next step, y2, is going to be y1 plus the step size plus my average again, and that gives me 5.640625. Step number 3 is going to end up being dy dx, but evaluated now at 2, 5.640625. So that gives me 3.640625. And so my y3 star is going to be the next point utilizing that slope, utilizing 3.640625. So that's going to be 7.4609375. Then my next dy dx at the next x, the next y, it'll give me this, 4.9609375. And then I use the average of these two slopes, this slope and this slope, the average of those two, in order to compute y3. y2 plus the step size times the average again. Our last step, our fourth step, is going to be dy dx at 2.5, 7.791015625. And that's going to give me this slope right here, 5.29, etc. I use that slope in order to calculate my y4 star, basically that next intermediary step, which ends up being 10.4365-ish. And then I get dy dx times 3, evaluated at 10.4365, etc. And that gives me this, the 7.436. And then my y4 then is going to be evaluated, there is my y3 plus h times my average, lots of numbers, and that ends up equaling, in this case, 10.973 approximately. So you can see we're just going to reiterate that process over and over and over again until what we end up with is we end up with my x value equaling the x value that I'm looking for, right? I'm looking for y of 3, so I'm going to stop at 3. In this case, we could evaluate the exact number of steps by simply taking 3, this 3 minus 1, those are my x's, and dividing it by 0.5, and that ends up equaling 4, and that's my n. That's how many n's that I'm going to need. When we use the modified Euler's method, we're using this actually for a very good reason, and that's because while Euler's method approximates the value of y of x given a dE, It's really sensitive to large step sizes, and there's a very real possibility for large error. When we use the modified Euler's method, we're going to do that approximation again, but it improves the estimates by improving our slope values. Our slope values are actually more accurate for the actual curve, and it decreases error significantly over Euler's method with only a very small difference in the number of computations. I know it looks way more tedious if you're doing it by hand, but if you think about this from a computing standpoint, if you're utilizing a computer, it's really only like 2 more computations per step, which is, from the perspective of a computer, is no difference at all, right? It doesn't actually change the runtime at all. And so consequently, we're gonna get a much better, much more accurate estimate without actually blowing up our computation numbers. I hope you enjoyed this video. I hope you got a lot out of it and learned a lot about modified Euler's method. And I hope you can use it inside of your differential equations classes, or if you need to go out and do some estimating or constructing some computer programs. If you did like it, go ahead and click on like. If you have any comments or you want to pop me a question, go ahead and put that in the comment section. And if you like the work that I'm doing and you want to see more of the mathematics or kind of keep up with the math that I'm doing on a regular basis, go ahead and subscribe to the channel.